Chapter 2 of the ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The ABC of Atoms by Bertrand Russell. Chapter 2. The Periodic Law. Before we can understand the modern work on the structure of the atom, it is necessary to know something of the different kinds of atoms as they appear in chemistry. As everyone knows, there are a great many different chemical elements. The number known at present is 88, but new elements are discovered from time to time. The last discovery of a new element was announced as recently as January 22nd of this year, 1923. This element was discovered in Copenhagen and has been christened hafnium. Each element consists of atoms of a special kind. As we saw in Chapter 1, an atom is a kind of solar system, consisting of a nucleus, which has electrons revolving around it. We shall see later that it is the nature of the nucleus that is characteristic of an element, and that two atoms of the same element may differ as to the number of their electrons and the shapes of their orbits. But for the present, we are not concerned with the insides of atoms. We are taking them as units, in the way that chemistry takes them, and studying their outward behavior. The word atom originally meant indivisible, and comes to us from the Greeks, some of whom believed that matter is composed of little particles which cannot be cut up. We know now that what are called atoms can be cut up, except in the case of positively electrified hydrogen, which consists of a hydrogen nucleus without any attendant electron. But in chemistry, apart from radioactivity, there is nothing to prove that atoms can be divided. So long as we could only study atoms by the methods of chemistry, that is to say, by their ways of combining with other atoms to form compounds, there was no way in which we could reach smaller units of matter out of which the atoms could be composed. Everything known before the discovery of radioactivity pointed to the view that an atom is indestructible, and this made it difficult to see how atoms could have a structure built out of smaller things, because, if they had, one would expect to find that the structure could be destroyed, just as a house can be knocked down and reduced to a heap of bricks. We now know that in radioactivity, this sort of thing does happen. Moreover, it has proved possible, by means of the spectroscope, to discover with delicate precision all sorts of facts about the structure of the atom which were quite unknown until recent years. It was, of course, recognized that science could not rest content with the theory that there were just 88 different sorts of atoms. We could bring ourselves to believe that the universe is built out of 2 or 3 sorts of things, or perhaps 3. We could believe that it is built out of an infinite number of different sorts of things. But some instinct rebels against the idea of its being built out of 88 different sorts of things. The physicists have now all but succeeded in reducing matter to 2 different kinds of units. One, the proton or hydrogen nucleus, bearing positive electricity, and the other, the electron, bearing negative electricity. It's fairly certain that this reduction will prove to be right, but whether there is any further stage to be hoped for, it is as yet impossible to say. What we can already say definitely is that the haphazard multiplicity of chemical elements has given place to something more unified and systematic. The first step in this process, without which the later steps cannot be understood, was taken by the Russian chemist Mendeleev. Mendeleev, who discovered the periodic law of the elements. The periodic law was discovered about the year 1870. At the time when it was discovered, the evidence for it was far less complete than it is at present. It has proved itself capable of predicting new elements, which have subsequently been found, and altogether the half-century that has passed since its discovery has enormously enhanced its importance. The elements can be arranged in a series by means of what is called their atomic weight. By chemical methods, we can remove one element from a compound and replace it by an equal number of atoms of another element. We can observe how much this alters the weight of the compound, and thus we can compare the weight of one kind of atom with the weight of another. The lightest atom is that of hydrogen. The heaviest is that of uranium, which weighs over 238 times as much as that of hydrogen. It was found that taking the weight of the hydrogen atom as 1, the weights of a great many other atoms were almost exactly multiples of this unit, so that they were expressed by integers. The weight of the oxygen atom is a very little less than 16 times that of the hydrogen atom. It has been found convenient to define the atomic weight of oxygen at 16, so that the atomic weight of hydrogen becomes slightly more than 1, 1.008. The advantage of this definition is that it makes the atomic weights of a great many elements whole numbers, within the limits of accuracy that are possible in measurement. The recent work of F.W. Aston on what are called isotopes, concerning which we shall have more to say at a later stage, has shown that, in many cases where the atomic weight seems to be not a whole number, we really have a mixture of two different elements, each of which has a whole number for its atomic weight. This is what we should expect if the nuclei of the heavier atoms are composed of the nuclei of hydrogen atoms together with electrons, which are very much lighter than hydrogen nuclei. The fact that so many atomic weights are almost exactly whole numbers cannot be due to chance, and has long been regarded as a reason for supposing that atoms are built up out of smaller units. Mendeleev, and at about the same time, the German chemist Lothar Meyer, observed that an element would resemble in its properties not those that came next to it in the series of atomic weights, but certain other elements which came at periodic intervals in the series. For example, there is a group of elements called alkalis. These are the 3rd, 11th, 19th, and so forth in the series. These are all very similar in their chemical behavior and also in certain physical respects, notably their spectrum. Next to these come a group called alkaline earths. These are the 4th, 12th, 20th, and so forth in the series. The third group are called earths. There are 8 such groups in all. The 8th, which was not known when the law was discovered, is the very interesting group of inert gases. Helium, neon, argon, krypton, xenon, and niton were all discovered since the time of Mendeleev. These are the 2nd, 10th, 18th, 36th, 54th, and 86th, respectively, in the series of elements. They all have the property that they will not enter into chemical combinations with any other elements. The Germans, on this account, call them the noble gases. The elements from an alkali to the next inert gas form what is called one period. There are 7 periods altogether. When once the periodic law had been discovered, it was found that a great many properties of elements were periodic. This gave a principle of arrangement of the elements, which in the immense majority of cases placed them in the order of their atomic weights, but in a few cases reversed this order on account of other properties. For example, argon, which is an inert gas, has the atomic weight 39.88, whereas potassium, which is an alkali, has the smaller atomic weight 89.10. Accordingly, argon, in spite of its greater atomic weight, has to be placed before potassium at the end of the 3rd period, while potassium has to be put at the beginning of the 4th. It has been found that, when the order derived from the periodic law differs from that derived from the atomic weight, the order derived from the periodic law is much more important. Consequently, this order is always adopted. When the periodic law was first discovered, there were a great many gaps in the series. That is to say, the law indicated that there ought to be an element with such and such properties at a certain point in the series, but no such element was known. Confidence in the law was greatly strengthened by the discovery of new elements having the requisite properties. There are now only 4 gaps remaining. The 7 periods are of very unequal length. The first contains only 2 elements, hydrogen and helium. The 2nd and 3rd each contain 8. The 4th contains 18. The 5th again contains 18. The 6th, 32. And the 7th, only 6. But the 7th, which consists of radioactive elements, is incomplete. Its later members would presumably be unstable and break down by radioactivity. Niels Bohr suggests that, if it were complete, it would again contain 32 elements, like the 6th period. By means of the periodic law, the elements are placed in a series, beginning with hydrogen and ending with uranium. Counting the 4 gaps, there are 92 places in the series. What is called the atomic number of an element is simply its place in this series. Thus, hydrogen has the atomic number 1, and uranium is the atomic number 92. Helium is 2, lithium is 3, carbon 6, nitrogen 7, oxygen 8, and so on. Radium, which fits quite correctly into the series, is 88. The atomic number is much more important than the atomic weight. We shall find that it has a very simple interpretation in the structure of the atom. It has lately been discovered that there are sometimes 2 or more slightly different elements having the same atomic number. Such elements are exactly alike in their chemical properties, their optical spectra, and even their X-ray spectra. They differ in no observable property except their atomic weight. It is owing to their extreme similarity that they were not distinguished sooner. Two elements which have the same atomic number are called isotopes. We shall return to them when we come to the subject of radioactivity, when it will appear that their existence ought not to surprise us. For the present, we shall ignore them, and regard as identical two elements having the same atomic number. There are irregularities in the periodicity of the elements, which we are only now beginning to understand. The second and third periods, which each contain 8 elements, are quite regular. The first element in the one is like the first in the other, the second like the second, and so on. But the fourth period has 18 elements, so that its elements cannot correspond one by one to those of the third period. There are 8 elements with new properties, the 21st to the 28th, and others in which the correspondence is not exact. The fifth period corresponds regularly, element for element, with the fourth, which is possible because both contain 18 elements. But in the sixth period there are 36 elements, and 16 of these, the rare earths as they are called, do not correspond to any of the elements in earlier periods. Niels Bohr has offered ingenious explanations of these apparent irregularities, which are still more or less hypothetical, but are probably in the main correct. Some very important facts, however, remain quite unexplained, notably the fact that iron and the two neighboring elements have magnetic properties which are different in a remarkable way from those of all other elements. The atomic weight of the earlier elements, except hydrogen, is double, or one more than double, the atomic number. Thus helium, the second element, has the atomic weight 4. Lithium, the third, has the atomic weight 7, very nearly. Oxygen, the eighth, has the atomic weight 16. But after the 20th element, the atomic weight becomes increasingly more than double the atomic number. For instance, silver, the 47th element, has atomic weight 107.88. Gold, the 79th, has the atomic weight 197.2. Uranium, the 92nd, has atomic weight 238.2. It is remarkable that X-ray spectra, which were unknown until a few years ago, show a perfectly regular progression throughout the whole series of elements, even in those cases where the order of the periodic table departs from the order of the atomic weights. This is a striking confirmation of the correctness of the order that has been adopted. The fact of the periodic relations among the elements, and of the progressive properties such as those shown in X-ray spectra, which we shall consider later on, is enough to make it highly probable that there are relations between different kinds of atoms, of a sort which implies that they are all built out of common materials, which must be regarded as the true atoms in the philosophical sense, that is, the indivisible constituents of all matter. Chemical atoms are not indivisible, but are composed of simpler constituents which are indivisible, so far as our present knowledge goes. Without the knowledge of the periodic law, it is probable that the modern theories of the constitution of atoms would never have been discovered. Per contra, the facts embodied in the periodic law form an essential part of the basis for these theories. The broad lines of atomic constitution will be explained in the next chapter. End of chapter 2.